All right, so welcome everybody to the 983rd monthly meeting. I'm sorry I couldn't be there today. I'm at a location 8 degrees in latitude for this week. Um, we have a speaker today, Brodi. Brodi, I couldn't meet you either. Hope you guys all had a good dinner, and hope that the clouds clear up after 2 o'clock. It looks like the clouds are clearing up after 2, so maybe you will be able to see the moon and the eclipse. So today, for Kerry is going to continue with the rest of the meeting, and Kerry, all yours.
Go ahead.
Yeah, is Rich Nugent with us?
He's online.
I am.
Okay, you and I talked about doing a little bit of experiment. Are you near a window by chance? You can take a look outside?
I am. I'm at a window that is 2,578 miles away from the parking lot at the Center for Astrophysics.
Okay, what's it like out there as far as daylight versus nighttime?
Well, let's see. There are some palm trees here. Palm
Yeah,
trees,
look it in.
but up in the sky, it's a little bit muted by clouds, but there's a bright star visible.
Wait a minute, it's daytime?
It is daytime here.
Oh, you're in California and it's daytime.
I'm in Chula Vista, California, and the sun is
I'm on
shining.
the other side of the country and it's nighttime.
He's on
For me, yeah, it is 5:30 in the morning.
Pay attention. If the Earth were flat, he'd be seeing it'd be dark there, or we'd be seeing the sun. So we have solved that here at Phillips Auditorium. The Earth is in fact curved. Thank you, Rich.
You're welcome.
And before we go any further, we talked about. I'm going to take just a second.
Too close.
Oh, okay. Is that better?
A little bit.
Oh no, I can't do that. Oh, I see what you're talking about. I didn't shave today. John Reed. I know a lot of you are familiar with him. He's been involved with this club for years. He's a very big figure in this club. And thankfully, I know, Al, you put a bunch of quotes that people had talked about him in the newsletter. So please check out the newsletter. You can see some of the things that he had done. What I was impressed that I didn't know is that he was a jet fighter pilot. And I guess he retired as a major. So he's always had these other lives we know nothing about. But I thought it'd be appropriate if we just take a moment of silence for John Reed, if you will. Thank you. Now let's see what's going on here. I have a trivia question for you before we get Rich on with what's going on with the solar system. I have a trivia question. Can anybody tell me a very important astronomical event that happened on this date, March 13th? Very important.
I know.
But you can't answer it just yet.
Oh, okay.
Nobody here knows, only Rich? Oh, we have to go all the way to California. I'd get too close. All the way to California. What's the answer?
March 13th, 1781, discovery of Uranus.
By William Herschel on this date, about 140 something years ago. Okay, I guess that's the point. We'll let Rich take over. You have some things to talk about as far as what's going on in the solar system?
Sure.
So
Mercury is rapidly leaving the evening sky after its March 8th greatest elongation east. I hope you've had a chance to catch a look at it. It reaches solar conjunction on March 24th and then enters the morning sky for a very poor springtime apparition. It'll as far away from the sun as it gets. The ecliptic hugs the horizon in the east in the morning in the springtime in the northern hemisphere. So get your Mercury fix in this week if you possibly can. Saturn and Neptune are currently lost in the glare of the sun, but Jupiter is one of the biggies in the sky these days. It's still around quadrature, 90 degrees away from the sun. So my suggestion is that you try twilight observations using a single element polarizing filter to improve contrast. See if you can see the moons of Jupiter when the sun is, the 4 Galilean satellites, when the sun is still up. That's a nice challenge. And a polarizing filter will help you with that. Mars, of course, is always a disappointment, it seems. 85 million miles away. It's only got a 10.3 arc-second disk, and it's still bright, but there's not much to look at. Venus is the real star of the show this month, and you know this has been coming. We've been waiting for this month for 19 months since the last inferior conjunction. Tonight, Venus is at magnitude minus 4.5. It's about 4% illuminated. Try daytime observations, try naked eye observations. If you're going to use a telescope in the daytime, I think the best way to do it is if you've got a well-aligned go-to telescope, that's pretty easy. But if you have a manual sort of pointing mount, whether it be an equatorial or an alt-azimuth, you can always offset from the sun. Just be careful of your optics. You're going to be pointing at the sun to get your 0 and 0, and then go from there. You can get the offsets from any planetarium program. Inferior conjunction occurs on March 23rd when it will still be at minus 4th magnitude, 1% illuminated, 8.5 degrees north of the sun. Careful telescopic observations are well worth the effort. It'll be less than 2% illuminated for plus or minus 5 days around inferior conjunction, and less than 1%, about 1% illuminated, be 1 day either side of inferior conjunction. So if the clouds interfere, you have a little bit of a window to check it out. Exquisitely thin, razor sharp crescent. And superior conjunction doesn't occur until way into January of 2026. So this will be a morning object until then. I have 2 slides to show next. One is by Maria. I don't think she knew I was going to put this on there. But Maria captured that telescopic view of Venus waving back at us not so long ago. And last week I was able to get a video, which I didn't embed here because I didn't think it would play. But there's a nice daytime shot of Venus. The air was really turbulent, which is why it's not the greatest of shots. But these are the sorts of views of Venus you can get if you go out in the daytime sky and check it out. Next slide here. Of course, we're all sitting on the edges of our seats, hoping that the skies later this evening are clear for the eclipse. I'm actually hopeful here out in San Diego. It was raining to beat the band this morning, which is super rare in San Diego. But the clouds are broken, and I'm hoping I get at least a little bit of a view of the eclipse. I get to see it 3 hours earlier than you all do. So hopefully you'll set your clock, and whether it be an alarm clock or a biological clock, to get up in the middle of the night and check out this eclipse. The next slide is the preview of the partial solar eclipse that's coming up 2 weeks from now on the 29th of March. It's a sunrise event. Sun in the Boston area comes up at about 6:30 in the morning, and fourth contact for the eclipse is at about 7:08. So it's a quick, not even 45 minutes, chance to look at the sun. Remember, safe solar viewing, and let's hope it's clearer on the 29th of March than it was back in June of 2021 when I took that shot at sunrise.
I'm just going to jump in, Rich, on that.
Yep.
If anybody here takes pictures of the eclipse of the moon and of the sun, send them to me, and we'll try to get them in the OC report next month. We'll display them. So if you do take a picture, forward them to me. Thank you. Okay, Rich.
Yeah, that'll be great. Hey, for the double star of the month, this is one you probably have never looked at before. I actually discovered this a few years ago, and I called Glenn and told him of my discovery. Cape Puppis is an absolutely spectacular double star. It's a little far south. You can see on that chart. It's towards the hindquarter of Canis Majoris, but it's another object that's well worth a search. Magnitude 4.4 and 4.6, 10 arc seconds. They're beautiful blue stars, and I highly recommend them. And as a bonus, Messier number 93 is just nearby. So that's the double star of the month. Notice I didn't put a variable star of the month, but we're keeping our eyes on, of course, T Corona Borealis, which is still waiting on that one. And the next slide, I think, is the February challenge. Glenn, do you want to do these?
Start digging back, though, to T Corona Borealis. When you're out tonight, if we have the clear skies, you have to be looking for the moon. Check that star out, because I got to feel probably pop tonight. Just to reward us, those of us that get up to look at the eclipse. Okay, we have some observers' challenges to talk about. The first one is NGC 1964. It's a spiral galaxy in the constellation Lepus. And I brought this up a couple of months ahead of time because it is very low in the sky, so there's a very small window to get to see this. And it was a February challenge, and we all know what the weather was like in February. It was terrible. I didn't get out myself, so I wasn't able to make a sketch of this. We had a couple of images. Now, this was the preliminary one from Doug Paul. It is a galaxy, again, in the constellation Lepus. We'll go to the next slide. And this is Mario Mata's image. And is Mario here? Apparently.
I'm in Florida, but I'm here.
Is it sunny or cloudy there?
It was a sunny day. I was imaging last night, in fact.
But right now it's cloudy there?
Partly clouds, but it should be okay later.
Okay, well, forget the flat earth thing. That wouldn't work on the same latitude, longitude line anyway. Okay, Mario, go ahead and tell us about that picture.
Well, let's take my 32. I took it in December because it's a small object, and it's just better through a larger scope. So that's through the 32. Because it's low in the sky, as you said, I didn't have the time window available to do a color image. So while it was highest in the sky, I think this was an hour and 15 minutes, if I recall correctly, of 5-minute subs. And I just went for detail rather than trying to get color. Taken with the 32 and a 6200 ZWO camera.
And by the way, this is about an 11th magnitude galaxy. Again, I didn't get a chance to look at it, but I would guess from my experience, a 4-inch telescope should pick it up if you're in a dark sky location. The nucleus itself is about an arc minute or an arc minute and a half by about a half arc minute, just this part. And this is what you see with a small telescope or even moderate-sized telescope. This is about 5 arc minutes across here and about an arc minute and a half, so that's what you pick up when you do imaging of it. Next slide. I believe we didn't get that many.
Glenn, can I throw something in, Glenn?
Certainly.
Just for reference, the 4 stars that are to the right of the galaxy in Mario's image, the brightest one is about 10.7th magnitude, and the dimmest one, I like that 3 of the curving arc of stars. I think the bottom one is about 11.5 magnitude. So those are 3 stars, 4 actually, if you can get the little one, that will be a nice sort of a guidepost to finding the galaxy. It's relatively easy to find, and those stars will be very helpful.
Okay, and Doug Paul? Doug is here.
Yeah. That's 3 hours with a 6-inch aperture.
6-inch. Okay, now the one for this month, currently, NGC 2419, it's a globular cluster in length. It's faint, kind of fuzzy, but it's very interesting because it's the most distant globular cluster that you'd be able to see with a normal backyard telescope. I think it's something like 250,000 light years from us and 300,000 light years from the galactic center. It's so far out there, in fact, it's farther than the Magellanic Clouds. So when its distance was first discovered, somebody thought this might be from another galaxy coming through our area. So it's called the intergalactic tramp. Now we call it the intergalactic wanderer. And I did check this one out with I think I used a 10-inch telescope. It's very faint, but I did see it not that long ago. The problem with it is it's in a rather barren area. This is the constellation Lynx, so I didn't have a nearby guide star. Again, I like the star hop. I don't have the go-to stuff. And I started over here at Castor, and I worked 7 degrees up to this particular area. And the funny thing is, what you see initially are these 2 stars right here, which are about 8th magnitude. And there was another star that's about 9th. They make a nice sweeping row that points to this area. And at first, with low power, with 10-inch, I didn't see anything. But I went to about 75 power, medium power. And I was able to see a very faint smudge. And of course, we'll be talking about that next month. But what I wanted to point out is right here, this neat double star. And that's one of the Struve double stars. And I'll talk about that one again next month. But this is a nice field if you find your way there. Again, if you were to go to telescopes, you'd be there right away. Just look for these 3 stars, and that's where you find the cluster. Again, the most distant one that we can see with a typical backyard telescope. The other ones are Palomar globular clusters. They're very faint.
Just a quick comment that the 2 blue stars to the right of the cluster.
We'll go back.
Yeah, those are blooms, so they're not actually as big as they.
But this was your preliminary. I make that
yeah.
point. What Doug does, he likes to send me a preliminary image, so I'll have something to show you. The same with the next image. We'll go to the next one. This is the one coming up. This is the April one. This we want to get a head start. And this is a combination. It's 2 galaxies, NGC 3893, 3896. It's a pair of galaxies in Ursa Major, right here near Chi. And they're right about up in here, just about 1.5 degrees away. The brighter one's about maybe 10.5 magnitude, so we got a 4-inch telescope to pick it up. The fainter one, though, is more like 13.5, so you need a bigger instrument. Images should be able to catch it fairly easily. But what's neat, and I'll talk about this again, we talk about this in April, but right below is a galaxy called 3877, which had a supernova, I think back in the late 1990s. So let's bring this all together when we get things going. But again, a nice target for imagers and a challenge if you want to try with a backyard telescope. And I think that's about all. Messier Marathon.
Well, I wanted to mention the Messier Marathon, and on the next slide, it gives our clubhouse schedule. But for any of you who've ever done a Messier Marathon, the mantra is start early and stay up late if you can. Typically, it's at the end of March, around the dark of the moon, and this month is perfectly suited to try out a Messier Marathon, or maybe not a whole marathon, because I don't know about you, but I can no longer stay up all night and observe. But if you work from about sunset, shows sunset is about 7:30 at night on the 28th of March. If you start early and you grab these four groups, we lost one of the arrows. Over towards the left is M77. I don't know where that arrow went, but it's gone. There's M74, there's M33, and there's the Andromeda group of M31, M32, and M110. If you grab those early, you can almost take a break because now you've got quite a bit of time to play with the rest of the objects. Those guys set quickly in the springtime. And the later we go, if you try it this coming weekend, or not this weekend, but the weekend after, you have a good shot at those. If you wait another week, it becomes even more challenging. Not to dissuade you, but Messier marathons are a lot of fun. They can challenge beginners, they can challenge veterans, and they're a blast. And Glenn and I will probably be hanging out at the clubhouse during the last 2 weekends of March in the hopes of getting some sort of a Messier thing going. Next slide, please. I think it just gives the clubhouse dates. So the 21st and 22nd, that's around last quarter moon. But if we do a 7:30 to midnight, you can almost pick up like 50 objects if you're quick. On the 28th and 29th, it's a new moon weekend. We'll try it again that weekend. And there are the dates in April, which will be way past the time for doing Messier marathons. So we hope to see you there. And Glenn, I think that's all for the observers report.
We're going to back up to, I was going to add something to the Messier Marathon. Then,
Go ahead.
Yeah, what we talked about, the last time we did one of these, I was involved, and Mike Brown is here, Mike did it as well. And it was kind of embarrassing. I was trying to get some club observing programs going. We talked about a double star thing and so forth, and it kind of fell flat. And it was embarrassing because I made a big deal about this Messier Marathon. And I forget, there was a club record, and I recall it was in the 90s. It might have even been John Reed. Somebody had it in the 80s or the 90s. And I talked this up, let's do a Messier Marathon. And it probably wasn't even this century. It wasn't the late 1990s.
Oh, when you and
The
I
one we did, yeah.
could have been.
And the problem is nobody could stay up past midnight. There was a bunch of us, most people left at midnight. Mike and I were full, and you left at about 3 in the morning. So I was all alone, and all of a sudden I could see voices and hear things in the dark. It was scary, but I got 99. And I'm going to brag maybe to just coax somebody into doing this. That's the record right now as far as I understand. If anybody's seen more than 99, stand now or forever remain silent. And I didn't get that 100th. I could have gone for M13, which is rather bright, but I was trying for M30. Those of you who know the Messier Marathon, that's a tough one. And I suddenly realized I should have gone for M15, and it was too late. It was already too, I thought I saw something, so I stuck at 99. I will not be able to do it again. I can't stay up all night long. So what Rich and I guess I thought about it more, was how about a Messier sprint? Instead of going all night long, like this first weekend, the moon's going to be in Sagittarius, so it's going to knock out. You're not going to do a complete Messier Marathon on that weekend. The moon will be right there. But the moon won't be rising until around midnight, so we could do a Messier sprint. And I'll put something out to see if anybody's interested. As far as people right here, is there anybody that think they might be interested in the Messier sprint where we give up at midnight? Just see how many. Okay. So I'll put it out there. It just might be fun. See how many you can see. I will tell you this. The one you want to catch first is you bring your binoculars and check the Pleiades. That's an easy notch right away. And then you got to look for other things that gets darker. Okay, I think Rich will let you take over now. Again, keep looking up. Thank you.
All right, Glenn, thank you.
Is this like doing the Appalachian Trail like in parts?
Well, I did have the thought of, Rich and I talked about, so we'll get together. We thought of maybe some type of thing that runs a year long. We will do a spring Messier.
There you go.
And so by the end of a year, everybody will see all the Messier objects. So it's kind of a thought. We'll put that out later on. Okay, thank you again.
All right, and with that, I'll hand it over to Brodi Elwood. We had a nice dinner, very engaging conversation, and Brodi will tell you about himself and start the talk.
Yeah, so I guess I'll introduce myself and then start the screen share. But yeah, so I'm Brodi Elwood. I'm a current PhD candidate at Harvard University in physics, and I work with John Kovac in the BICEP Keck collaboration, and we work on ATMoB polarimeter, so measurements of the cosmic microwave background, the cold relic light. And I'll be discussing today my work on characterizing the optical response of these telescopes, what you may know in true visible optics as the point spread function in radio length, tend to call it a beam, and the kind of a discussion of how these optics are designed for radio and the material selection that goes into designing these beautiful instruments. All right, so I'll go ahead and share my screen. I think that should just work. Okay, all right. Sorry. Technology is happy today. So yeah, today I will talk about the design and characterization of optical systems in the microwave. Just so that we're all on the same page, I'm sure most everybody here is familiar with. Please get very good. With radio astronomy in general, I want to start off with a brief introduction, somewhat concise, but kind of an overview of radio astronomy and how you build radio telescopes. So what kind of science can be done with in the radio, and what kind of techniques are employed in radio detection and construction of radio telescopes. And then I want to move to a more specific case study of the telescopes I work on, the BICEP Keck cosmic microwave background polarimeters, and such as just have a conversation about the cosmology that is involved in understanding the CMB, what the CMB is, why we care, and how do we measure it. And then kind of finish off, I'd be remiss if in front of this group if I don't advocate for you too can do amateur radio astronomy. You can build your own amateur radio telescope. It's a lot of fun, I promise. Okay, so that we're all on the same page. The thing we all know and love, the electromagnetic spectrum. So what is, there's two words in there, right? Electromagnetic. So electromagnetism is this one of the forces of nature, and it's the primary force of nature for which we interact with the world, right? We have eyes that see through the electromagnetic spectrum. And all of our lived experience is kind of in this slice of the electromagnetic spectrum, and about 400 nanometers up to 800, 900, depending on your eyes. And all the telescopes that you see pretty pictures of, stars and amazing pictures you guys take, and images and science is done, and historically has been done in just this band. But the electromagnetic spectrum is quite a spectrum, and it's quite a bit larger than that. And so what happens when you go a little bit lower energy, or higher wavelength, or larger, longer wavelength rather, or lower frequency? These are, in the visible, the size of the waves, the size of from peak to valley in the electromagnetic wave for the visible is, on the size of things like bacteria and smaller, pinpoints and needles. Whereas in the radio, you actually have your waves around the size of even, little animals, people, entire buildings, up to kilometers in size. So there's this whole other side of the spectrum at which we can explore the universe using signals and light that come from this end of the spectrum. And then down here, due to the fact that things that are hot like to become cold, one of the mechanisms by which things cool down, right, is radiating off. And this means that anything with a non-zero temperature has what's called a black body spectrum. And that makes a one-to-one correspondence between the electromagnetic spectrum and something's temperature. And so in the radio, we often talk about how bright something is, and something called a brightness temperature. This is just saying if this thing was a black body, how warm would it be given the where we see it in the spectrum. So how do we pick up these radio waves? Let's take take it back in time a little bit just to discuss the history of the development of radio astronomy. It's obviously quite a bit different than the development of optics, in that the telecommunications industry is really where this became a thing. So early 1930s, Karl Jansky, working at Bell Labs in Holmdel, New Jersey, decided that he might be able to pick up what he calls electrical disturbances in the sky. So he built this apparatus here, which is a very fun thing to look at as an astronomer, a radio astronomer over almost 100 years later. And what this is, what you're seeing here is, it's got a gantry system and tires so it can be rotated, but all these, his detectors, or rather his antennas, are these metal poles here. So he just strung up a bunch of wires on this gantry system. And what he did is he picked up a signal from the Milky Way, which was the first kind of detection of radio waves outside of Earth. And I really like this article here. This is original 1933 article, Electrical Disturbances Apparently of Extraterrestrial Origin. I think it's thing I think is enjoyable is the electrical disturbances. This also points out the kind of correspondence between electrical engineering and radio engineering, because radio engineering is really kind of a subset of electrical engineering. And
what was the asterisk about? Did he kind of hedge his bets there a little bit? Or?
That's a good question. It might be annotation. I don't remember actually. That's, should go read that paper. But yeah, this really shows that the kind of history of radio engineering comes from these were electrical engineers at heart, and that the kind of language that radio astronomers use really is adopted from that. And that's important for how you design these telescopes, because a lot of the design is really feels like electrical engineering, and that's like optics sometimes, although there is still a lot of optics involved. Alrighty, so, oops, just want to throw up this slide real quick. Okay, so we start with these telescopes that are just wires on a gantry, and we can move around. Jump ahead 30 years, still at Bell Labs, due again to the pressures in the telecommunication industry, they wanted to get very faint signals in different locations on Earth. So they started building these big concentrators. So this kind of starts looking like a telescope. You've got a mirror here that takes in light, redirects it and concentrates it into a kind of a readout system, and then amplifies it, and you can pick up your signal at the other end. And this started the kind of development of the kind of cornucopia of radio telescopes we have to this day. And wanted to point out here, I talked about this correspondence between temperature and the electromagnetic spectrum. So we're talking about the various components of this telescope. We typically talk about it's like antenna temperature, for instance, so it's the equivalent temperature. If you're going to replace that component with a resistor, what you see electrically at the other end.
Sorry, but in that chart, the sky, that is the microwave background?
Yeah. So this is an internal Bell Labs report, which I highly recommend if you're a history buff. Go to the internal reports for Bell Labs that are published, and they have this beautiful one that came after the discovery of the cosmomicrowave background, which is what that's trying to describe there, and it's pretty cool to see. So yeah, we have this thing, and jumping ahead another 4 or so decades, we have this cornucopia of radio telescopes, many of which you're probably familiar. This one down here is near me. I'm from Arizona, a family from New Mexico. This is a very large array in eastern New Mexico. Various other telescopes over here. You got Arecibo, which is the big famous telescope of Puerto Rico. Former telescope, that unfortunately collapsed. And then there's a Green Bank telescope, and keen eye will notice that thing kind of looks a lot like a satellite dish. Optically, it's basically the same as a satellite TV dish. It's a prime focus off-axis parabolic mirror telescope. And then the one that's near and dear to me now is down here, the BICEP Keck telescopes, which are at the South Pole, and I'll go into detail. But I wanted to continue going through what makes a telescope, and tie this into, the radio telescopes are really just doing the same thing. So what makes a telescope? Well, at most general level, you need a light collector. So this is your aperture. You gotta collect at least some photons. You probably won't collect them all, unfortunately. You need a concentrator. Typically this is as a lens, but in radio we have a thing that acts like a concentrator and a feed horn that kind of, if you from the Bell Labs figure, you got a mirror and a thing that concentrates. It's typically called a feed horn. And sometimes you have a mode matcher, which is the thing that takes your electromagnetic waves from free space into some waveguide system. So the analog and optical will be like fiber optics. We call these waveguides in radio. And then you need a detector. And detectors in the radio are very diverse because the dynamic range of the frequencies that we deal with, all the way down from sub-millimeter all the way to waves that are in kilometers in length, the kind of microphysics of detecting these waves varies quite a lot. But at the end of the day, imaging optics just map points in object space, the points in image space, and that means angles become images, or angles become points, your focal point. So just to kind of hammer home that it's all the same electromagnetic spectrum, and that you can conceptualize of radio telescopes in the same way that you can think about optical telescopes. Here's a full Maxwell wave simulation of just a lens. And so what you're going to see is plane waves coming in. So these are kind of waves that come in from, let's say, stars with a very flat phase fronts. You're going to see a plane wave generated here, go across the lens, and then you'll notice there'll be a single point that it concentrates it down to, which we call the focus. Just play this real quick. So the plane wave, it hits the lens, it gets bent by the lens because the lens has a higher index of refraction than air, and it gets concentrated out. So these are the type of simulations that we use in astronomy to understand what our telescopes are doing. So what makes a radio telescope? My point is basically exactly the same process. You take light in, you do some stuff to it, which I'll discuss in detail with the telescope that I'm most familiar with, and then out comes science. And what is some of the science that we do with it? And that is, particularly that's the ALMA, one of the ALMA receivers, which is an interferometric array in Chile. But before that, the astute observer may have noticed that, okay, what determines the resolution of the telescope? The Rayleigh criterion, which is a function of wavelength and the size of your aperture. So as you go up in wavelength, you actually go down in your resolving power. And to resolve something like Jupiter, which is fairly big on the sky, 30 arc minutes, at 1.42 gigahertz or 21 centimeters, just as an example, you'd need a dish almost 100 meters wide. So could you imagine trying to build something like that? You won't be able to do that in your backyard. So how can we get around this problem? What if we take measurements of the electromagnetic field from different receivers separated far apart? So we just sample the electromagnetic field at different places with different receivers. Will this help us out? Before we understand why that might work, we need to think about another property of the electromagnetic field, which is that of coherence. So who is familiar with Young's double slit experiment? Probably almost everybody. So this is another EM simulation, full wave simulation of Young's the Young's double slit experiment. Again, you'll see plane waves, coherent plane waves. So waves that are all in sync, and we have a precise timing relationship between them. Starting on the left, propagating to the right, and then they are interrupted by two apertures in this screen. And these two points then act as sources themselves, and they interfere to give you the famous diffraction pattern. So we do this with pointing at the famous ones, like point a laser, and then you get a diffraction pattern. That's what you're seeing here. You're seeing kind of peaks and nulls. And anybody know the spacing between these? What does this tell us? It tells us the resolution of this particular system. So resolution is also encoded in here. But more importantly, this feature of these diffraction patterns doesn't show up if the waves coming in aren't coherent. So this was how this was done historically, interestingly, by Young in the early 1800s, was he took sunlight, which is somewhat coherent, but not all the way, put it through a single slit, which makes it coherent, and then put it through a double slit. And I realized when I did that procedure, I get this nice wavelength pattern. Okay, why is coherence important? Coherence is essentially the fact that electromagnetic waves have a magnitude in the phase, so they have some total intensity information, and they have information about their timing, about when they arrive. And we call in what you call measuring both the magnitude and the phase is coherent detection. And coherent detection, going through all this exercise, is coherent detection is much, much easier in the radio than it is in optical. And this makes, I think this is one of the key differences between just the practical applications and design of radio telescopes, is the fact that we even have a hope of doing this. And this is, I mean, at a high level, it's basically because electromagnetic waves at these frequencies can jiggle electrons in wires, or sorry, in metals, and we can easily read out voltages. And voltages have a nice sign, can have nice sign-like components to them, where you get the magnitude and the phase information. So, what can we do with this? Radio interferometry, which most radio telescopes you've maybe seen, or you've even seen pictures of products from radio telescopes are probably from an interferometer, because most single dish or smaller telescopes just don't have a resolving power to resolve anything interesting. So we can exploit coherent detection to cheat by measuring all the electromagnetic waves at different locations, and either with the same clock or with many very accurate clocks, we can collect that light and then merge the data later. And then in a process called forming synthetic aperture, we can form what I said, effective larger aperture, which is given where the resolution is given by the distance between the telescopes and not the size of any individual telescope, which gives us much, much higher resolutions. So the kind of granddaddy in this space is the telescope I mentioned earlier, VLA, a very large array in New Mexico. It's made up of 27 20-meter dishes, so still very large dishes. They're spaced up to 34 kilometers apart. And what this gives, even though individual dish can't resolve to that level, the array is allowed to can resolve to 1/10 of an arc second. And the VLA does a wide range of science, measurements of radio galaxies, quasars, black holes, and whatnot. The image in the top up there with the kind of blobs. In 1987, the VLA was actually the first instrument to measure the Einstein rings from lensing. So you may know if you have a massive object that sits between you and something emitting radiation of some sort, in this case radio, the light will bend or diffract around that gravitational field. And the radio telescope was the first telescope to kind of pick this up, which was also a key prediction of general relativity, and very exciting. And then you may have seen this picture. This is, or a picture like it, of this particular one is of Characterize A star, which is the supermassive black hole at the center of our galaxy. This object is extremely tiny on the sky, right? It's just a single object, but it's very massive. So how can you resolve that? How can you help with resolving this with radio telescopes that have this measure with very long wavelengths? We do this interferometric technique, and in this case, the EHT that measures that took this picture essentially, the Event Horizon Telescope, is a consortium of telescopes that use the same optical systems, but kind of ship around clocks and receivers. Take these measurements and then ship all the data back. So they literally shipped all the data back on hard drives. And then because they have the magnitude and phase information, they were able to correlate it and through a bunch of other math, produce an image of what you would see if you have eyes big enough and are able to see in the radio, which is very exciting. It's the first picture, well, the second picture of a black hole. The first one was an M87. Radio astronomy serves a wide range of science. I had some other telescopes I wanted to talk about, but in the interest of time, I think I'll skip over those unless other people want to discuss them. There's the Green Bank Telescope, which is the one that kind of looks like a satellite dish. There's also Chime, which is an interesting telescope because its optics are very different. It has cylindrical parabolic mirrors and what's called a focal line instead of a focal plane, because all the light is concentrated on a single line. and just has a very unique optical system. But in the interest of time, I'll skip over those for now. Yeah, I was just hoping to give kind of an overview of the general framework of optical or of radio telescopes and how they really are just optical imaging systems. And the detection, works differently. We can do this in a ferrometric technique, unlike an optical where you have really no hope of sampling the phase information of the optical electromagnetic wave. So this technique's a little different, but then I'm going to kind of transition into talking about a specific telescope that also has very unique optical chain that I'm more familiar with and that I directly work with in terms of determining its optical characteristics. But before I move on, are there any questions related to what I covered so far?
I had a question on the previous images. Is that imaging the Hawking radiation near the black hole? What is, what are we actually looking at here?
Yeah, actually, so this is what's known as the photon ray. So this is just all the things falling in and getting hot.
I see.
And then the light, of course, is bent around it because of very intense gravity. These images are used not just to point at and look pretty, but their general relativity predicted what these should look like. They checked out there, and there's other features that once you get more resolving power in these telescopes and these very long baseline, what's called very long baseline interferometry, longer baselines, so for bigger aperture, you'll start resolving little features in there, and there's very interesting science in terms of the interaction between general relativity and magnetism for this particular black hole. There's other features in there that they're hoping to resolve the next generation of this particular telescope or collection of telescopes.
Yeah, so it's my understanding that the radio telescopes are almost always 1 pixel at a time that you're sampling. So you're doing this interferometry. Does that mean that all the telescopes have to be pointed within that fraction of an arc second?
Yeah, so it's true that a lot of these these interferometric telescopes are single pixel instruments, although the VLA is also, but not all. The interferometers tend to be single pixel instruments because you're looking at getting a bunch of different pixels spread out. So you want to build kind of cheaper, just a really good pixel, pick all that up. That's what I kind of brushed over. But the kind of image here is to show that these have to be pointing very accurately in the same direction.
That's all done mechanically, or is there something else that you do to try to adjust for getting that spot on?
I'm not an expert in this particular niche of radio instrumentation, but from what I understand, it's essentially they have very good models of the mechanics of their telescopes. They do things like pointing checks with objects that have known positions. Some of these, I believe, the VLA or one of the arrays in the United States uses satellites for beamforming. So they watch a satellite track across and make sure it's in the same position as we'd expect.
Okay, thank you.
Now I want to jump into a case study of the BICEP Keck CMB polarimeters and why we care about them, and the kind of intricacies of measuring the cosmic microwave background, especially the polarization of the cosmic microwave background. So your question that usually radio telescopes are single pixel. Well, this is has one of the densest focal planes. Has some of the most pixels of any radio telescope out there. This is a very unique design because of the science that we do, which is something I want to go into. So I have to take a step back to describe, to motivate why we want to build the instrument I'm about to describe. So just a brief history of time in one slide. What we got here is, if you start with general relativity, so if you assume Einstein is right, which is good, probably a good assumption because normally we've already discussed in science has verified the validity of general relativity in many regimes. But if you take general relativity, you apply the cosmological principle, which is this assumption that the universe is isotropic and homogeneous, meaning if you look at any single block of the universe on large enough scales, it basically has the same amount of stuff in it. And you look at any angle in the sky, it pretty much looks the same in any direction at very large scales. Of course, at smaller scales, there's lumpy things like planets and people. But if you assume that, out pops an expanding universe, which you may know as the Big Bang model, or what we call the standard model of cosmology. And what this means is the universe has a thermal history. And if you go roll back time and start at the beginning, the universe started in a very small, dense, hot state. But then as you go back forward again, as the universe cools, it goes from being very optically thick, so think of like a plasma, right? Very hot plasma, it's charged, the electromagnetic waves don't have a lot of freedom to move very far because they're kind of bouncing around all the electrons. But as the universe cools, those electrons settle out into atoms, and the photons, the electromagnetic waves, are all of a sudden able to free stream. And essentially takes a picture of what the universe looked like about 380,000 years after the Big Bang. And that light has been traveling to us for about 13.7 billion years. And in that time, it has been stretched out by this same expanding universe to be cooled down to about 2.7 Kelvin. So there's a remnant of the Big Bang, which we call the cosmic microwave background. And this is a cold radio background that is everywhere in the sky. When I mean cold, it's about 2.7 Kelvin, so just a little bit above absolute zero. And relating that back to, okay, what are the radio waves emitted by this thing? What is the wavelength of these photons? About 2 millimeters, 160 gigahertz, which is a signal of a relic black in the Big Bang. Interesting, this microwave background is a near perfect black body because it comes from the early universe, which is just this big hot thing. It's basically just a big black body. But there are ripples in this thing, which is where all the science from the CMB comes from. And this is a very famous image of the Planck satellite, which was a CMB instrument that took an all-sky map of the cosmic microwave background. And what you're seeing in here are little ripples in around 2.7 Kelvin, about the millikelvin level, one part in 100,000. And why this is interesting is this model of the Big Bang doesn't really account for what we call the horizon problem. So you can imagine, you look at a photon coming from that direction in the sky, and a photon coming from that direction in the sky from the cosmic microwave background, you can wonder, how did that one know that one wanted to be at 2.7 Kelvin? Because that's what we see. That side of the sky is at 2.7 Kelvin, that side of the sky is at 2.7. Now why do they agree to one part in 10,000? Well, the answer is, the possible answer is, maybe at some point in the past, they were actually in contact with each other. They were close enough that light could interact and they could equilibrate, as we say, to the same temperature. And so this leads one to posit an extension to the standard model of cosmology, that if something causes the early universe to be in an energy state where it suddenly expands, then things that were once very close together all of a sudden become very far apart. This rapid expansion moves regions that were once in contact with each other, then out of contact. And we call this inflation, so you might have heard of inflationary theory. So you imagine this process of inflating a universe by just an insane number. It's like 10 to a really scary number in a very small amount of time. This is a very energetic process. This stretches space-time, incredibly stresses space-time, and so this produces gravitational waves. Right? So we might have heard of gravitational waves in the context of like an image down there, LIGO, which directly observed these gravitational waves using optical interferometric techniques. And so these are similar gravitational waves, are not sourced by things like black holes, but are sourced from inflation. We call these primordial gravitational waves because they come from the early, very, very early universe. Okay, so we can posit this and okay, well, what are we going to do about it? How can you can just make up any theory you want. What is the prediction of this? And to understand that, we got to talk about polarization real quick. So I know you're all familiar with optics, so I won't belabor this point too much. But polarization is just the fact that photons, for instance, have a spin, and so they have a direction in which they're oscillating. And we call this the polarization vector. And just in terms of day-to-day experience, if you've ever been to a lake and you put on sunglasses, which are polarizers, that filter out certain polarized photons, you'll see, without the glasses, you'll see lots of bright light from the lake. what the glass is, that'll go away. And that's because these photons, as they scatter off or reflect off the lake, are polarized in a certain direction. Your sunglasses delete that, essentially. Or if you put on your glasses and you look at your rearview mirror and you see little speckles in the glass in the back of your car, this is polarized effects in the glass. There's stresses in the glass that cause polarization. Okay, so light has this other property, in addition to coherence and other things we talked about, called polarization. And these primordial gravitational waves that I was talking about can imprint particular signatures in the polarization by mechanisms where they stretch, gravitational waves, when they pass by, compress and stretch space-time in particular ways that imprint themselves in the cosmic electromagnetic background polarization in patterns that we call E and B modes. Don't even know the particulars of those. That's just some way of which we measure these fields. And a measure of the power in the in these primordial gravitational waves is a number we call R, the tensor to scalar ratio. And that is the number, because it's a measure of the primordial gravitational waves, which in turn come from inflation, something like inflation. This number R is important, and I'll talk about why we build the telescopes we do to maximize our chances of measuring light. Okay, so what do the actual data look like? Just so again, at a high level before I drill down into the telescope. We take what are called angular power spectra, that's really the technical term, but the easy way to think about these are going back to that image of the cosmic electromagnetic background where it's got a bunch of ripples in it. You can ask, okay, if I take this point over here and that point over here, and I compare them, how much are they alike? And that's a point on here. So if you look at different scales, if you then kind of increase your scales of like, well, I'm looking at micro-arc-minute scales, I'm looking at degree scales, I'm looking at tens of degree scales, and I look and see, oh, how much is the temperature correlated on those scales? That's that top curve there. And so these are what are called the primary anisotropies of the cosmic electromagnetic background, and a lot of science is done up in those ripples over there, which are called the baryonic acoustic oscillation, which are sourced by pressure waves, essentially sound waves in the early universe. But the thing I want to point out in this plot that's important for what we're about to discuss is notice the temperature is all the way up there, and the E and B modes are down here. I guess something I didn't explicitly mention was primordial gravitational waves are the only source of these E modes here, of this particular polarization state. And that means if you measure polar B modes, that's a smoking gun of inflation, with the proviso that there are things in the universe aside from the cosmic microwave background. And so lensing B modes, I talk about the discovery of Einstein rings in the VLA. Well, these Einstein rings, or the kind of bending of light around massive objects, can actually blend these E modes into B modes. And so these show up as a false signal. So there is a foreground there. We call it foreground. But at the end of the day, we want to design an instrument that is able to pick up this very faint signal down here, or this one down here. So these different blue lines are for different levels of theory of whether or not the primordial gravitational wave is a little more powerful or a little less powerful. And you notice this peak is right around, if you look at the top scale here, right around degree scales. So going back to that resolution problem, generally in radio you need a really, really big aperture to pick anything up. We don't really care about resolving power very much in this case, because the peak we're looking at is about degree scales. So this means we can build small, compact telescopes. And we call these small aperture telescopes. And these are refracting telescopes that are located at the South Pole. And why the South Pole? Well, South Pole is high and dry, believe it or not, it's a desert. So there's not a lot of water in the air, which is very important for radio. It's one of the problem with radio is we have to deal with water a lot. We can observe the same patch of the sky, which is a kind of a cold spot in the southern galactic plane, like the hemisphere rather. And we can observe it continuously because we're at, the Earth is a sphere, and you can just continuously scan the same region. And so I mentioned the polarization of the electromagnetic field. And so how we actually do polarimetry or the science of measuring polarization is by taking two co-located orthogonally polarized detectors. So it's a bit of a technical term, but you just imagine a detector that can see light that oscillates this way and a detector that can see light that oscillates this way, and then you subtract them and that gives you a measure of polarization. So that's what we mean by pair differencing, because we have detectors that live on the same chip. And I'll talk about our detector design in just a second. But I promise for telescope makers not to throw up the optical train. Some things that are important to point out in this type of design is these telescopes, as I said, are compact, small aperture, and I guess I didn't explicitly say what small aperture is, but you can kind of wrap your arm around these things. They're about 55 centimeters in diameter, so not very big, as radio telescopes go. I had mentioned before also that everything that has a temperature emits electromagnetic radiation, and things that are warm at like the human level, so room temperature, emit a lot of radiation in the exact same wavelength that we're looking at here, which is a big problem. So what we have to do is we have to encase our entire telescope in a cryostat, meaning that our optics all sit at cryogenic temperatures. And so we have various filters which block out infrared radiation that we don't want, sitting at about 50 Kelvin, and our lenses are at 4 Kelvin, and then in addition, our detectors rely on superconducting physics to do their measurements. So those set actually at sub-Kelvin temperature. So just go over this optical chain again. We have, because it's a cryostat, it's in vacuum, right? You gotta suck all the air out in order to, you don't want a frozen block of oxygen. So you gotta pull all the air out, so we need a vacuum window. So this is a very nicely designed vacuum window. That sits at 300 Kelvin, so the only component that sits at 300 Kelvin. And then some filters and two lenses that focus light onto a focal point. So overall, pretty straightforward optical train with some interesting details that are specific to radio. So for instance, I'll belabor it here, but if people are interested, I'm happy to talk about it, okay, so anybody know what materials these lenses might be made out of? Or it says here, so maybe you can cheat, but they're made out of plastics, right? Polymers. Glass is opaque in the radio for the large, more or less. Polymers are clear, so if you could see in radio, you'd be able to see through plastic. That's why like things like wireless network access points are all encased in plastic. It doesn't actually interfere with the radio waves at all. Plastic is clear. So these optics are all made of plastic, and I'm happy to discuss how we select those materials. I work on a project that deals with the selection of those materials and characterizes them. But moving on, how do we actually pick up this radiation? So I said we take this light, focus it down like you would any two-lens refractor into a focal point. And here's where we do something interesting, and why I mention these interferometers is we have what's called a phased array. And these are a bunch of detectors that are sampling the focal plane, kind of like the detectors of an individual interferometer would. And then we have sampling, meaning they take the free space electromagnetic waves, pipe them into little wires, because we can do that in the radio, and then add them all together, and then deposit them on what's called a transition edge sensor. These are a superconducting bolometer. So a bolometer is really just a resistor, a thermistor. And so the light gets focused in, it gets coupled in by these phased array, which are just little antennas, little dipoles, and then it gets fed into the actual sensor, which is really just a bolometer, a thermistor. And when the light comes in, it drives up that resistor, and that's a detection of a photon. If anyone wants more detail on exactly how this detectors work, I can go over that. So what problems do we face when building these telescopes? Well, first, as I said, the signal is faint. It's nanokelvin scale. And we have to see the CME through an instrument, which we're not, is a challenge. We're not just given these values of polarization from God. We have to see it through an instrument. That's what I'm trying to demonstrate up here. You know, you have start with the Big Bang, and then you get the CMB, and then you have all these things in between you and the CMB, and then finally you have your telescope, which itself has a response. And you've got to characterize that response in order to make an assessment of your measurements. So, last thing I'll finish up with is how we characterize the optics of these telescopes. So, just bring it back to things everybody here is probably familiar with are point spread functions. So, point spread functions are you take a telescope or any optical system, point it at a point-like object, so something that's not resolved, it's below the Rayleigh criterion, and measure the response that comes out. So, pop quiz. Does anybody know whose point spread function this one is? This telescope. Which telescope that comes
James
from?
Webb?
Yeah, it's James Webb. And you know that probably from all the little hexagonal patterns here, because it's made of a hexagonal, kind of a hex array mirror, a segmented mirror. What about this one? This might be a tricky one because you've probably seen the real images of it, and this is just a simulation. It's had all the gross things in there. This is Hubble telescope. You might be able to tell from the kind of arms. It's kind of got this arm to hold the primary obscuration. And then this one is just a diffraction pattern from just a telescope that has a circular aperture. So if you have no obscurations, you're just a bare mirror, you'll get this kind of point spread function. So this is how the telescope responds to a point in the sky. So these are just the aperture functions with these the apertures look like. So before I jump into details of what I do in particular, we've actually borrowed a technique from amateur astronomy for characterizing our telescopes. We take a single aperture Hartmann mask. We measure the point spread function of the beam for at least 2 rotations of this mask. And then the shift in the pointing of that beam, so how much that beam moves around, is a measure of how out of focus the system is. And so we use this technique. It was inspired a collaborator, Matthew Petrov here, is when he came up with this idea. We used these measurements to refocus one of our telescopes and achieve a Strahl ratio of about 0.99. So it's very, very diffraction limited. It's very, very exciting. So finally, getting to my last point here is how do we actually measure the point spread functions of something like a radio telescope, or the beams of a telescope? So point spread function is something that comes from the telescope just looking at a point-like object. Well, unfortunately, point-like objects at the South Pole that are easy to see for our frequencies are kind of hard to come by. Jupiter's not always up, it moves around, things like that. So what we can do, because our far field is actually not that far away, so another formula you might be familiar with is, how long does it take you for your the rays coming from your telescope to be collimated? In the radio, it's pretty short actually. It's only about 200 meters for our aperture size. And so we can put an artificial source on another building at South Pole that's not that far away, and then we can chop it. We can blink it at a certain frequency. And what this does is we can just pick up that frequency, and that rejects all the noise that might be sitting around. So what I mean by that is you get something that looks like this. So this is a real photograph from the telescope, one of the BICEP 3 telescope looking at one of the other labs down at South Pole. What you see here is a ground shield, so this is just supposed to block the telescope's view from the partially from the ground. And there's our source up there, so it's really, you can't really see it even in the photograph. And then this is the same image taken by the telescope itself. So this is talking about, it kind of shows you how many pixels we have, right? We can take a single snapshot of the South Pole, and so you can see the same structures, right? Here's we've got the other telescope over here, and then kind of the mass. But if you notice, well, we're trying to take the point spread function. Where's the point source of it? Unfortunately, you can't see it because we haven't demodulated. We haven't taken out that, picked out that frequency that was chopped out. So what I show here is you take all of kind of the signal chain of this telescope. So I mentioned we've got all these foregrounds. You come in and you measure the telescope. It gets focused on the focal point, sampled by the phased array, and read out by the and detected by the transition edge sensors, and we get a bunch of time strings for all these detectors, about anywhere from 2 to 5,000 detectors on a focal plane. And then we just take our knowledge about the pointing of the telescope, rearrange the data, the time stream of the data, and then pixelate it into images. And then now we got a nice source here. And so that's our beam right there. And why am I belaboring this point of beams? We particularly care about beams in this instrument because of this thing that I pointed out of the hot temperature sky, this kind of that line that's really large versus the little signal that we're looking for. Well, I also mentioned that we measure polarization by taking one direction and subtracting another direction. Well, you can imagine that if this direction has an intrinsic response different beam than this direction, and what this is going to do is going to bleed hot temperature sky into cold polarized signal, which is not something we want to do. So what we do is we take all our beams measurements for a year, so we have something on the order of tens of thousands of these types of images of the beam response of the telescope. We add them all together to get a nice beam for each detector, and then add them together again to get a beam for the entire telescope. And this allows us to compare our results to external maps. Yeah, so I guess this is in math what I just said. So what I want to point out here is that any difference in the beam response of the co-located detectors comes out as a polarized signal. So up here we have A and B are the beam responses, and you just take A minus B, and the T term should drop out. But if A and B are slightly different, the T term doesn't drop out, which is the kind of the entirety of the problem here. Why this matters is even, say, a 1% leakage of this very hot signal can dominate our signal in polarization. So how do we mitigate this? We mitigate this by taking our beams, so these very fine measurements of our beams, we subtract them, and then we take out, we subtract them and then we take out we call the leading order mode. So these are the things that we know about the optics and the shape of distortions between the beams. We basically fit those out doing a fitting procedure, a filtering procedure. And then what's left over, we take that, so we take our beam, or basically actually this beam, this leftover beam, and then we reobserve the temperature sky. So we take another map from, say, Planck, that same map that that I showed earlier. We reobserve it with our constructed beam, or as measured beam. And then since it's only temperature, we then ask how much polarization is left over. And what we get is an upper bound on how much polarization is bled, or how much temperature is bled into polarization by the imperfect matching of our beams. And a measure of this is, I mentioned this tension to scalar ratio, kind of tying it back to the actual science, is this shows up as an effective bias on R, but an effective misestimation of R due to something intrinsic to the telescope itself. And so this is currently our leading order systematic, instrumental systematic, and it's about a factor of 10 below our noise floor, our noise level of our measurement on R. So it's an important thing to study. Important thing to understand the optical response of our telescopes. So the last thing I want to finish on is just a brief conversation on how you too can join the fun in amateur radio astronomy. Before I jump into that, to finish up with that, are there any questions about BICEP Keck, CMB polarimeters, or beams measurements, point spread functions, or the science of the CMB?
Hi.
Go ahead.
Yeah, I'm Charles Wright. I'm online here. And I was wondering, how many pixels is this? And also, your wavelengths you're receiving are in the microwave range, which is I'm not. I mean, that can range quite a large range of wavelengths. So I'm wondering, are your actual pixel sensors on the order of like a half wave, like a dipole, or are they somehow smaller? And how do you get that density, basically?
Yeah, so yeah, I brushed over the details of our instrument, but the BICEP Keck program is a series of currently 5 telescopes at the South Pole. One of them, getting this image here, pointing at the bottom right. This image is of the BICEP array as it was 2 years ago. We have receivers that are 30, 40 gigahertz, which is combined in one receiver. We have a receiver at 95 gigahertz, which is the BICEP 3 receiver.
Okay.
We have a receiver at 150 gigahertz, and a receiver at 220, and a receiver at 270.
Okay, so that's like millimeter waves then.
Yeah, so these aren't quite microwaves, more millimeter.
Okay, thanks.
Yeah, and they're spaced that way, just to give some background, like why those frequencies. It's the lower frequency receivers, so 30, 40 gigahertz, pick up the foreground that's from synchrotron radiation, so electrons moving through the magnetic field of the galaxy. The 95 and 150 gigahertz are the primary CMB channels, and they're spaced that way actually because there are dips in there are spectral lines all throughout between 30 and 300 gigahertz from things like oxygen and water, and 95 and 150 sit just between those, and are also kind of near the peak of where the CMB is. The CMB peak is about 2 millimeters, 160 gigahertz, so those are our primary CMB channels. And the 220, 270 receivers are for picking up what astronomers lovingly call dust, which is basically all the stuff that isn't stars, that sits around and mucks up our pretty data. So that's the spectral response of the spectral shape rather of the dust is, the 220, 270 receivers are designed to pick that up and do that, what we call foreground separation. Okay, yeah, any other questions? Just jump into a brief discussion on amateur radio astronomy and what happens when you combine a ham and a telescope. Okay, yeah, so this is just a single slide, and I was hoping to have a conversation, and right now and after, on designing your own radio telescope. So radio telescopes have optics, just like you're very familiar with. It's not grinding mirrors, unfortunately, but it's building things like this, or even just finding one on eBay. You can buy a Ka band dish that's about this size and the same focal length and primary focus. Parabolic reflector. You can find a feed horn, which is really just a fancy word of saying a collector that contains your antenna. And you can also pick up cheap detectors these days. So thanks to the ever-evolving telecommunications industry, cell phones, computers, and whatnot, software-defined radios are incredibly cheap these days. And software-defined radios that can measure in the low gigahertz range are cheap. I mean, like $30 cheap. Of course, you can buy better ones for hundreds or even thousands of dollars. But you can do basic things with $30 after. These are things that are just USB port, a coax cable to your either your amplifier or your LNB or low noise block, and you're off to the races for things like 21 centimeter astronomy. Or you could be ambitious and do something like amateur interferometry, where kind of the optimization calculus changes, where you want to have many smaller cheap dishes that you can then spread apart and think about how you would do something like correlation, which is the process of making a synthetic aperture and converting your visibility information into actual images. What I've got shown here is, you're all, of course, familiar with Haystack. This is Haystack builds an amateur and has like a very, very thorough guide on how to build amateur radio telescopes of this design. And the first telescope I actually ever touched was this one. Well, not this exact physical one, it's the one at MIT on its roof. It's the same design. And yeah, it's a pretty easy system to use, and they have really good documentation on it. And the one on the right here is kind of more akin to the receiver I showed at the third slide. That's a horn, and so it's basically just imagine like those old ye old earphones, right? It's what it's doing for the electromagnetic waves. It's kind of catching them and bringing them down to a point where you can feed them into something like a waveguide. And this is built by a student here at Harvard for a class that my advisor teaches, and but this thing is just just a bunch of metal that you can kind of rivet together, weld together, and then buy a cheap low noise amplifier and an SDR for readouts. So yeah, I mean I think this is if you're interested in both optics and somewhat electrical engineering, amateur radio is really the way to go. Unfortunately, you're not going to take beautiful pictures of things like even planets with telescopes of this size, but things you can do is an interesting measurement you can actually make with this receiver, the 21 centimeter, is what's called a galactic rotation curve, which is actually the measurement that was told us that dark matter likely exists. So there's cool measurements you can do even with these size of radio telescopes. So yeah, hope that was a good grand tour of radio astronomy and kind of give you a flavor of what we do as radio astronomers and how it's very similar to what optical astronomers do and are concerned about with their telescopes and areas where it's different. One thing I kind of brushed over to really what I alluded to was just how different the material selection is. It's like the optical telescopes benefit greatly from the fact that the larger industry really cares. There's a lot of investment, right? How camera companies, the government, famously the Hubble telescope came from the National Reconnaissance Office. So there's a lot of people who care really a lot about building really good cameras. Radio less so. And so our thought process on selecting materials is a little different, and it's kind of more in-house, if you will. So that's something that I also deal with in my research, and I'm happy to discuss at length too. So, that's all I had. And if there are any other questions,
Did you talk about amateur interferometry? How would that be? How would that be done? I mean, are you thinking of something like crowdsourcing, or?
You'd have to worry about things like pointing.
Yeah, that's exactly why I asked that earlier.
Yeah.
Because I had that idea in my head. I was like, amateur interferometry, how would you do that when pointing is so difficult?
Yeah.
So they have to be pointed in the same direction at the same instant, is that it?
Yeah.
Yeah, right.
They have to be pointed very
What the individual antennas, you don't have to judge the beam width of the rest of the resolve part.
Yeah, so I mean, you've got a little bit of wiggle room for the beam size.
Could you
but
just
yeah,
rely on the rotation of the Earth? Instead of panning the antenna, could you just point it in a fixed direction?
Yeah, exactly. That's how many of the early arrays work. I mean, arrays that work to this day.
I see.
You lose the rotation of the Earth to kind of scan across the sky. But yeah, this is. I mentioned this because there's not a lot of. It doesn't seem like there's a lot of people doing this, but I think given where the technology is at and just how cheaply you can build these types of telescopes.
Yeah, it seems well within like high school range,
Yeah, I mean, like I'm working my way through trying to see if I can come up with like a receiver that I can build on like a graduate student budget myself. And Corona didn't really talk about explicitly was, so you've got to take all this data and then combine it somehow in what's called a correlation process. You got to reconstruct the electromagnetic field. That's incredibly computationally intense. And historically, like the first interferometers, they were like hand-built analog computers, and then they kind of upgraded to digital, and they're still very, very hand-built. But now with the advent of things like high-power GPU acceleration, you actually have a whole lot of computing power in your day-to-day PC. That's kind of built for this type of operation. The type of math that you need for doing this correlation is exactly what GPUs are built to accelerate. So there might be a space there where like amateurs can get involved because they can now build correlators very cheaply with this high performance computing that we all have at our fingertips.
Or do it in the cloud.
Or do it in the cloud. They can rent something and do it there. Yeah. So if anybody here is a software engineer, that's okay. Yeah, no. Welcome. There are a lot of open source codes for things like correlators, which I think will be very fascinating to work on. Yeah. So yeah, thank you. I'm very happy to be here. I'm happy to discuss more. You can reach out about the work I do, and I'm happy to discuss other aspects of my research and what amateur telescope makers can do in terms of radio astronomy.
Thank you. All right, well, thanks for coming tonight, and we hope to see you next month, on April 10th, for our 984th monthly meeting. Safe travels, everyone. Good night.
Thank you.